In this section, we're going to take a high-level look at what WebAssembly is and how we can use it in Rust. WebAssembly, abbreviated as WASM, is a binary instruction format for a stack-based virtual machine. It is designed as a portable compilation target for allowing deployment on the web for client and server applications. WASM is designed to be efficient and fast by executing at native speed and taking advantage of common hardware capabilities available on a wide range of platforms. Like most concepts, the best way to gain an understanding is to see it and then do it, so let's jump into using Rust by starting out setting up our environment to allow us to use WebAssembly. The first thing we are going to do is install WasmPack, which is a one-stop shop for building, testing, and publishing WebAssembly created by Rust. And luckily, it's a very easy install for us. Just head to rustwasm.github.io/wasmpack/installer. And if you are on Windows, which I am, then you will just download and run this executable. But if you're on Linux, then you run this command down here and follow the on-screen instructions. So I've already installed it, and it's a very quick install. So once you have installed it, then continue on with this video. So the next thing we are going to install is Cargo Generate. And this is going to help us get up and running quickly with a new Rust project using a template that we can get from a Git repo. So to install it, we just run cargo install cargo generate. And I've already installed it to help with the time of this video. It will take a couple of minutes or so to install, so please pause the video and then resume it once you have completed the installation. And then once you have Cargo Generate installed, then the last thing we need is npm, which is packaged with Node.js. So head over to the Node.js website and download Node. I have downloaded the latest long-time support version, which at this time is 16.15.0. So that's what I recommend as well. And then one thing to do when you have finished installing node/npm, I recommend just exiting out of Visual Studio Code and then restarting it, because node and npm will be added to your path variable that the terminal uses. So in order for the terminal to get the new path variable, I would just recommend restarting Visual Studio Code. That way you have access to npm and node from the command line. And that's all we had to do to get set up using WebAssembly. So now we can start creating our first project using WebAssembly. So we are going to run cargo generate tac-tac-git, and we're going to get a template from the Rust WASM GitHub. So it is github.com/rustwasm/wasmpack template. And it will pull it down for us, and it's going to ask us for a project name. I'm going to name ours WASM Game of Life, because we are going to create the game of life to get an understanding of how WebAssembly works. And I'll explain what game of life is in the preceding lectures. So you see that we have a bunch of files and a couple of directories generated for us. And if we look inside of source and then librs, we see that we have an extern block with an alert function in here. And if you come from a JavaScript or TypeScript background, then this might make you wonder, okay, is this referring to the JavaScript alert function? And it is. So we're able to access the JavaScript alert function using an extern block and then referencing the function name. And so what we're going to do by running this template is we're going to call our greet function inside of our our WASM executable per se, and our greet function is going to call on the JavaScript alert function, and we're going to print out hello WASM game of life. So in order for us to run our WASM, the first thing we need to do is change into our new directory, which mine was WASM game of life, and then inside of here we're going to run WASM pack build, and it's going to compile for us, and it's going to generate a new directory for us called package, or PKG for short. And inside of PKG you see that we have a bunch of additional files created for us. And inside of our package directory, as I said, you see that we have JavaScript, TypeScript, which we can now work with on getting into a web page. So inside of the directory we're currently in, we're going to run npm install, or excuse me, npm init for initialize WASM app, and then www. And this is going to give us a new folder, a new www folder that's really important for us. So we need to switch into that directory and run npm install. And npm install is going to install the Webpack JavaScript bundler and its development server. And once it's completed, we now want to reference our WASM project. So for us to do that, we go into the www folder. We're going to go into this package.json file, and below home page and above dev dependencies, we're going to add a new dependency for ourselves. And ours is going to be the name of our project, so WASM game of life, and then we're going to reference where it's at. So from here it is up one directory, and then inside the package, that directory that we generated using WASM pack build. And then once we do that, we can head over to we'll save that file. We can head over to index.js inside of our www directory, and up here we're going to say WASM game of life. So now we will run npm install again, and it will install our WASM game of life dependency, and now we can run npm run start. And we see that we compiled successfully. So now we can head over to our browser and go to localhost 8080, and we see that we have the hello WASM game of life alert, which, if you remember, is what we did here, right? So we're using the JavaScript alert function, and then inside of our index we see we have wasm.greet, and we are calling our Rust function greet. And so now we have successfully set up, built, and ran our first WebAssembly project. So what we will do from here is now we will go and create the game of life. That way we can really dive into how WebAssembly works when we use Rust. Conway's Game of Life, also just known as Life, is a cellular automation game created in 1970 by John Conway, a British mathematician. This game has a few rules that we need to be aware of prior to beginning creating the game. The first rule is any live cell with fewer than 2 live neighbors dies, as if by underpopulation. Any live cell with 2 or 3 live neighbors lives on to the next generation. Any live cell with more than 3 live neighbors dies, as if by overpopulation. And then lastly, any dead cell with exactly 3 live neighbors becomes a live cell, as if by reproduction. So we can condense these into the following 3 rules. Any live cell with 2 or 3 live neighbors survives. Any dead cell with 3 live neighbors becomes a live cell. And then all other live cells die in the next generation. Similarly, all other dead cells stay dead. So those are the basic rules for creating the game of life. And so now let's talk about how WebAssembly and Rust and everything just kind of interacts, and some of the things that we need to take into consideration when using Rust to create WebAssembly. So for our game, we are going to create a fixed size periodic universe where cells on the edges have neighbors that wrap around to the other side of the universe. Because neighbors wrap around the edges of the universe, gliders can keep running forever. And one of the first things that what I want to clear up is what WASM bindgen is. So you can see it here, and you can also see it here in our template. It is a common understanding of how to work with compound structures across this boundary. So it involves boxing Rust structures and wrapping the pointer in a JavaScript class for usability, or indexing into a table of JavaScript objects from Rust. So WASM bindgen is very convenient, but it does not remove the need to consider our data representation and what values and structures are passed across this boundary. Instead, think of it as a tool for implementing the interface design that we choose. So there are 2 things that we should always be thinking about to optimize. So we want to minimize copying into and out of the WebAssembly linear memory, because unnecessary copies impose unnecessary overhead. And then secondly, we want to minimize serializing and deserializing. Similar to copies, serializing and deserializing also imposes overhead, and often imposes copying as well. If we can pass opaque handles to a data structure instead of serializing it on one side, copying it into some known location in the WebAssembly linear memory, and deserializing it on the other side, we can often reduce a lot of overhead. So WASM bindgen helps us define and work with opaque handles to JavaScript objects or boxed Rust structures. So in essence, by using WASM bindgen in this instance, we are exposing the greet function to our JavaScript. And then as a general rule of thumb, a good JavaScript WebAssembly interface design is often one where large, long-lived data structures are implemented as Rust types that live in the WebAssembly linear memory and are exposed to JavaScript as opaque handles, aka using the WASM bindgen. JavaScript calls exported WebAssembly functions that take these opaque handles, transform their data, perform the heavy computations, query the data, and ultimately return a small, copyable result. By only returning the small result of the computation, we avoid copying and/or serializing everything back and forth between the JavaScript garbage collected heap and the WebAssembly linear memory. So that is just something to take into consideration. It's a very important aspect that I really want you to understand. So if you're still a little iffy on it, please re-watch this lecture again. And then if you have any questions, please ask them in the Q&A section, because knowing when to use this WASM bindgen is really going to help you organize your code, help you think, far ahead in your project, and it will help speed up your overall the overall performance of your project. So now that we have that in the back of our mind while we're creating our project, let's begin creating our game. Alright, so let's begin creating our game. So I just want to start by cleaning up a little bit here. And now we can start off by creating our cell. And we're going to want our cell to be exposed to the JavaScript. So let's go ahead and use WASM bindgen to expose it. And we want it to be represented by an unsigned 8-bit integer, and then we're going to need to derive a couple of traits. So the couple of traits that we're going to want, I say a couple, we're going to want many traits. We're going to want clone, copy, debug, partial, EQ for equality, and EQ as well. And now we're going to create an enum called cell. And then inside of here we're going to have dead equals 0 and then alive equals 1. And so to expand on the repr U8, that's important because we want each cell to be represented as a single byte. And so the next thing we can define is our universe, which is also something that we're going to want accessible inside of the JavaScript. So we're going to say pub struct universe, and then inside of here we're going to have a width of an unsigned 32, a height which is also unsigned 32, and then we want our cells to be in the universe as well, which we will represent as a vector of cells. And so now that we have our universe defined, we can start implementing some methods on it. The first method we want to implement is accessing the cell at a given row and column into an index into the cell's vector. So we will implement some methods on our universe. And again, we want to be able to get an index into the vector. So we'll create a getIndex function. We're going to pass in self, and then we have our row and our column. And we're going to return a usize. So the logic in here is going to be pretty straightforward. We're just going to return the row times our self dot width plus the column, and we want to return it as usize. And that's all we need to do in order to get our index. And now that we have the method implemented, we can calculate the next state of a cell. So we need to get a count of how many of its neighbors are alive. And the method is going to use deltas and a modulo, which is the percent sign. And we're using that to avoid special casing the edges of the universe with if statements. So we're just trying to avoid having extra if statements when we don't need to do them by using this logic. And so by applying a delta of -1, we are actually adding -1 to the height, and then we mod it. So this allows us to avoid unsigned integer underflow, meaning we went below 0, and since it's unsigned, our results would be incorrect. So let's start implementing this, and this will make a little bit more sense. So we're going to say our live neighbor count. Again, we're passing in our self, our row, and our column. And we're going to return back a U8. So we'll say let mutable count equals 0, and then for delta row in self dot height minus 1, 0 for the row, 1 for the column, and then we are going to iterate, clone, and now we're going to do the same thing for the row. So we're going to have the column, delta column in self dot width minus 1, 0, 1 dot iter dot cloned, and then if delta row is equal to 0 and delta column is also equal to 0, then continue. So now down here we can say let neighbor row is equal to the row plus delta row mod self dot height, and let neighbor call equals column plus delta call mod self dot width. And then our, we'll just go idx for index, self dot get index of our neighbor row, and then for our column, neighbor column. And now we can add to count self dot cells at the index as a unsigned 8. And then all we want to do when this loop is done is return our count. So all we're doing is getting the count of all the cells located, of all the neighbor cells located at that row and that column inside of our universe. And so now that we have that done, we have everything needed to compute the next generation. And we can have a straightforward implementation of the game's rules by using a match expression. And since we want JavaScript to control this portion, we are also going to place this inside a WASM bindgen block. So let's go ahead and add it. So we have WASM bindgen, and now we're going to impl universe again because we want this to be exposed to the JavaScript interface. And now inside of here we're going to create a function called tick, and basically a tick is a new generation. And so we're going to pass in our self, and now inside here let mute next equals self dot cells dot clone. And now we can say for row in 0 to self dot height, and for call in 0 to self dot width, we can say let idx equal self dot get index of our row and our column, and then let cell equals to self dot cells of our index, and then let live neighbors equals to self dot live neighbor count of our row and our column. And now we can start implementing in the rules. So let next cell equals match on the cell and the live neighbors. So we have rule 1, which is any live cell with fewer than 2 live neighbors dies because of underpopulation. And so we can say cell alive X if X is less than 2, then cell is dead. And now we have, we'll put another rule 2. Any live cell with 2 or 3 live neighbors lives on. And we'll just go ahead and write out the rest. Rule 3, any live cell with more than 3 live neighbors dies because of overpopulation. And then rule 4, any dead cell with exactly 3 live neighbors becomes a live cell due to reproduction. So now let's implement rule 2. So we have cell is alive 2 or cell is alive 3. Cell alive. Okay, so now we can implement rule 3. So we will have a cell alive if X greater than 3, then our cell is now dead. Excuse me. Alright, we have a little error here. What do we... oh. There we go. And now we can implement on rule 4. So our dead cell, if it has 3 neighbors, now becomes a live cell. And then otherwise, because remember, you have to handle all situations, otherwise all cells maintain themselves. Otherwise, cell remains in the same state as before. So now we can end that block, and then we can have our next iteration on the next index equals to our next cell, and we can say self.cells equals to next. So currently we don't have any way to display the game currently. So we need to implement a method that will make this easy for us to see what is going on when we execute our program. We will use empty and full squares to signify if a cell is dead or alive. So just copy and paste the symbols from the code that I provide you. So we need to use standard format, and down here we're going to implement format display for our universe, and in here we're going to have a formatting function going to refer to self, and then it's going to have a mutable formatter, which is going to return a result for us. And so in here we have for each line in the self.cells as a slice dot chunks self.width as usize. And then for a reference to our cell and line, we're going to say let symbol equals to if cell equals to is equivalent to a dead cell. Then we want a empty, and I'm just going to copy and paste this in for myself, else, there we go, else we want that guy. So let me format this real quick to make it pretty. Alright, so let symbol equal if cell is equal to dead cell, then we want if the cell is dead, we want an empty square, else if the cell is alive, then we want a full square. That is correct. So now we want to write F and then symbol, propagate if there is an error, and now again write, but this time we just want to write out a new line character. And return OK. Alright, so it doesn't look like we have any errors, so everything seems very happy with that. So now we have a way to display out our universe. So I'm going to take a quick pause right here, that way this lecture doesn't get too terribly long, and we will pick up in the next lecture. Alright, so just a quick recap on what we have done so far. We created our cell, we created a universe, we implemented a method on getting our index, that way that we can create or count the number of live neighbors our cell has, and then our tick method, which we exposed via bindgen so that the JavaScript is able to access this functionality, is just allowing us to implement the game of life rules on whether the next generation of cells are dead or alive, depending on the 4 rules that we got. And then we also implemented a way in for our program to display our dead cell or our live cell. So we're pretty close to being done with implementing this game. There are 2 more methods that we need to define. And one of the methods is our constructor, which is going to initialize our universe for us. So we're just going to call this new, and it's going to return back a universe for us. So we know that we need a width, and we also know that we need a height. And our universe struct up here also needs cells. So now we have to add in our cells. So we're going to just do a random assortment of where our cells will be. So we're going to do cells from 0 to height times width, so 64 times 64. Since that is the size of our universe, that is how many cells we need to have. And then we're going to map these values, and what we're going to do is say if I mod 2 is equal to 0, or I mod 7 is equal to 0, and you can change 2 or 7 however you like. Those are just the values that I happen to pick. If I mod 2 or 7 is equal to 0, then our cell is going to be alive. Otherwise, our cell will be dead. And that's just going to give us a random placement of cells onto our universe for us. And then we want to collect those values. That way we have a vector of them. And in here we're going to create our universe with our width, height, and our cells. Alright, so it looks like I have a little error. What am I forgetting? Map. Oh, it helps if I put it inside. Oh, not parentheses. There we go. Okay. And just to make this pretty, I'm going to do cargo format. That way we follow the standard formatting. And then lastly, the last method we need to define is our render, and that is going to just refer to self, return a string, and self.toString. So this is all that we needed to do inside of our librs. So now, with us having made changes to this, we're going to run wasm-pack build, and everything compiled successfully, which is great. So now that we need to just do a couple of additional setups. So we'll go over to our index.html file inside of our www directory, and we are going to add in a pre-tag, which is going to create a element on our web page called the Game of Life canvas, and we want to make sure that that element exists before we try to draw our universe. And then I also want to add in some styling. Again, just copy and paste this in. I'm not going to go over the CSS styling behind it. So from the code that I got you, just feel free to copy and paste it in. And that's all we need to do inside of index.html. So I'm going to close that out. I'm also going to close index, our package. So now inside of index.json in our www directory as well, I went ahead and cleared out this file, so you can do the same if you want. But otherwise, I'm going to import in our universe from our WASM Game of Life. And then inside here, we're going to want to get access to the element that we added into our index.html. So we named it the Game of Life canvas. And now we want to go ahead and create our universe. So we will say universe.new. And universe.new is referring to our new method that we created here, and JavaScript is able to see it because of the WASM bindgen that we gave this entire implementation block on the universe. So the way that this is going to run is that the JavaScript is going to use a request animation frame loop, and then on each iteration it's going to draw the current universe by calling on the universe tick method that we implemented right here. So we can implement this by saying we're going to have a constant render loop. We'll do an anonymous function, and we will say pre.text content is equal to universe.render. Render, again, referring to the render method that we implemented right there. And now we are going to say universe.tick And now we're going to request animation frame on render loop. And then to get this to run for us just the first time, we are going to execute a request animation frame on render loop, and then that will put us inside of our loop. So now we need to change directory, so cd into www, and now just to make sure that we have all of our dependencies installed, we'll run npm install and wait for it to finish. Alright, and now we can run npm run start, and it looks like it's compiling. It compiled successfully. So now if we go to localhost, refresh the page, and we now have our game of life implementation working. So you can see we have live cells here because we have the full squares, and then all the empty squares are dead cells, and you can see that all of our cells are just interacting. And you can let this run for as long as you want and watch how your universe continues to change and how the cells continue to come alive and or die based on the rules that we implemented. So congratulations on getting this working. Hopefully you can see that working in WebAssembly is actually pretty straightforward overall. I hope you enjoyed creating this little game and have a much better understanding on how to use WebAssembly as you dive further in on your journey with Rust. Please feel free to ask me any questions in the Q&A section if you have any.